everybody. We're getting ready to kick off our second presentation. Today we have Dr. Arshang Angoshtare. Did I say that right? And he's from Naval Surface Warfare Center, Carter Rock Division. Today he's going to be talking about near-term hybrid quantum classical framework for the finite element method. Arshang made the trip out from DC. He's a resident at Bethesda. So thank you for joining us, Arshang, and please, over to you, but please say a few words about yourself first.
So hello everyone, this is Arjang Angoshtari from Naval Surface Warfare Center. Let me go here. Okay. First of all, thank you to the organizer for the invitation. I have three hats at my command. So I'm leading our massively parallel finite element simulations for the target strength branch. I'm leading deep learning application development for acoustic signature division, and I'm leading our quantum computing effort at the command. So I'm going to give you an overview of what we're doing at Carter Rock regarding quantum computing. So this is the overview of my talk. So I will go quickly about the main aspect of what we're doing there, and I'm going to provide some reasoning why we choose a specific application for our quantum computing application. Then I'm going to talk about basic aspects of quantum computing and this application that we think is more important for us, which is finite element method for solving differential equations. And based on that, I'm going to talk about a near-term quantum classical solution for what we're doing. And just to provide some challenges that we may face, I'm going to show some numerical results, and then I'm going to through this future goals and challenges that we face. Okay, so let me begin with some general remarks. So at Carter Rock, we are dealing with ships and submarines at different stages of their lives. And that means that we are doing too many different types of simulation. And naturally, we are interested in any approach like quantum computing that may allow us to do our simulation more efficiently. And this is also consistent with the current assessment for the impact of quantum computing on the military impact of quantum computing, which says that although the existing quantum computers have very low military impact, it is expected that a full-scale quantum computer will have very, a high impact on, military impact. So one thing here about our organization is that unlike some other naval organizations like specifically NRL and NISQ PAC, we don't have very established experience or history in doing quantum computing. So for us, when we wanted to start our task in fiscal year 2024, one question is that how we are going to get it started. In that regard, we consider some of the good suggestions that are available out there, like these ones that I put there from McKinsey and Company. Regarding getting started, for example, I put these 5 items there. I'm going to read from it. Actively screen quantum computing use cases and follow quantum computing developments. Understand the most significant risk and directions and opportunities. Consider whether to partner or invest in, this quantum computing player. And here it is mostly software, of course. And the other thing is recruiting in-house quantum computing talent. And the last one is to build digital infrastructure to meet the basic operating demands of quantum computing. And then the other thing is that, important question is, what is the viable quantum computing applications here? So several factors to consider here. One is that, is it possible to solve math problems behind business challenges with known quantum computing algorithm? So the reality is that we have a limited number of quantum algorithms, something like, 100, something like that. And mathematically, you can show that any problem that can be formulated classically can be also solved with a quantum gate. some sort of quantum circuit, actually. But the point here is that you may not get any speed up or any advantage out of that. So here there are two concepts that we should realize. One is this quantum utility, and the other one is quantum advantage. So quantum utility means that you simply show that you can solve something with quantum algorithm. Quantum advantage is that you are going to get really something out of that. When people talk about quantum advantage, people are thinking mostly about some sort of exponential speed up or something like that. But I'm going to give some examples that even if we don't get any speed up, quantum computers may be useful. Okay, the other question to consider when choosing application is that how much speed up is, for a practical advantage over a standard, these HPC systems are good for us. And the other one is what kind of quantum hardware for that speed up. So right now, we have this so-called NISQ computers, these noisy intermediate scale quantum computers that you cannot, I mentioned that we have something like 100 quantum algorithms. We cannot implement many of them on existing machines. So the question is, if you want to have some near-term application, we should focus on algorithm that can be implemented. Summarizing this point, one thing that is obvious is that you need some sort of expertise in both quantum computing and the specific industry that you are dealing with. And this is a challenge. Right now, apparently, we don't have sufficient, this is not very well-established field. Specifically, when you go into these specific fields like naval applications, some of which are not being taught in any university. So then the challenge is that how you're going to get both expertise, and this is related to workforce development. Some details about our quantum computing project. So this is supported by this so-called NISQ programming of warfare centers. So this is some sort of internal.
NICE funding is experimental funding, is that correct?
This is more for 6.1, 6.2, 6.3 type of activities, but it should be spent only on internal research and development.
Perfect. I just wanted to clarify, since probably not everybody knows what that is. Thank you.
Yeah. The main goal of this project has been workforce development. As I mentioned, this is an important aspect of being able to utilize quantum computing. And the other one is identifying potential naval application for our command. And the last one is developing tools. And when I say developing tools, I should say that our focus here is near-term application. We want to know what we can do with quantum computing now, not thinking about some theoretical algorithms that can't be implemented sometime or anytime. So regarding the workforce development, there has been some, there are some observations here. It is hard for us to hire quantum computing expert, both with or without domain-specific expertise. Our short-term demand most probably doesn't justify that we hire someone that is, without any domain-specific expertise in our domain. So that is the reality for us. So a consequence was that we established a team which consists of current command employees, which have expensive domain expertise, but no quantum computing expertise. And finding these type of people is also another challenge. One reason is that these folks are typically triple booked, so hard to convince someone to come, specifically when this is dealing with very risky field. They may have spent 4 years on this, and there may be nothing out of that. So hard to convince folks. And then regarding the learning approach, this has been a combination of self-study and getting a master's degree and using this certificate in quantum computing. Regarding applications, so there are several applications, well-established and less well-established quantum computing applications. So perhaps the most famous one is this encryption, and this quantum chemistry and optimization, but there is also applications in nuclear and particle physics and machine learning and differential equations. The first thing that we did, we contacted all departments at our command and asked about the computational needs, what they think is a challenge. And the main response that we got is that finite element simulation, this differential equation, is our main application. So to clarify, what do I mean? I can give an example here. So imagine, consider this ship here, and imagine that you want to model the effect of this explosion on the structure of this ship. So first of all, this problem is huge. Imagine that you want to consider a mesh for the ship itself, and then you need to also consider a mesh for the fluid surrounding that. So this is a huge problem. But this is not the only problem. The main issue here is that this problem has some sort of a stochastic nature, in the sense that you don't know exactly the location of explosion. You don't know the power of that explosion. You don't know environmental factors there. So this means that one simulation is not sufficient here. You need several simulations. And the challenge here is that when each simulation takes something like 2 weeks, how many of them you can have per year? If you want to have some meaningful gain here, perhaps you need several hundreds, but of course you cannot have several hundreds of 2-week simulation in a year. So this is a challenge here. So the main point here for us is that a small quadratic speedup here is useful for us. So by that I mean, so let's say a 2-week simulation can be reduced to, I don't know, 2-day simulation. So I'm not, my concern here is not exponential speed up, so I don't think, I mean, it is good if we can reduce 2 weeks to less than a second, which is what is typically advertised for a typical exponential speed up, but here we have a more modest goal. So to give some more details about this application that we care about, so imagine that we want to do a simulation which has something like 2 billion unknowns. And this number is not something random. It is related to a specific simulation that I personally doing right now. And I think this is among the largest in our command. So if you want to do simulation of a problem of this size on a DoD HPC system, you need something like 500 standard nodes. If you want to do this with a quantum solver, it may require only 31 qubits. And this 31 qubits comes from the fact that 2 power 31 is 2 billion. And some algorithms that I'm going to talk about, they work based on this law, let's say. So if you look at the quantum computers that currently exist, I listed 6 of the IBM quantum computers that we have access to. So all of them have more than 127 qubits. So this 31 qubit looks very accessible. And let me clarify something here. When people talk about solving differential equation with quantum computers, basically they are talking about breaking the ceiling or something. So they are talking about Navier-Stokes equation, turbulence equations, turbulence phenomena, or this weather prediction models with 1 meter resolution that involves trillions of unknowns. So those type of problems are things that we cannot do right now. But what I'm discussing here are the problems that we can do right now, but theoretically we can do them. But I'm going to mention some challenges that some modelers like me face. That means that practically we may not be able to do them. So this is the sense that I think that even with no significant speed up, this quantum computing can be useful. So I mentioned that in this above example, we need something like 500 standard nodes for the simulation. But the reality is that many of the available HPC solvers, specifically the local one, doesn't have 500 nodes. So this is one thing to consider. The other one is that even those that has more than 500 nodes, like some typical HPC servers, they have something like 1,500 nodes. And imagine that you want to reserve 1/3 of a system for a simulation, and this is also not easy. And the last one, which is, I think, the most perhaps compelling reason why this quantum computing, even with no speed up, can be useful, is that, so we have different classification for data, confidential, secret, top secret. And depending on the specific application, we have some extra classification as well. I'm talking about ACCM, this NNPI, RD, additional limits. And one challenge here is that you cannot process, for example, secret ACCM with secret RD. So this is it. You need to process them separately. And that can be a problem because, so remember that we have some many HPC servers that do not have 500 nodes. These are typically local servers that are, used mainly to process a specific type of data. So going back to the example that I mentioned that needs 500 standard nodes, imagine that it is related to, I don't know, some sort of submarine that is ACCM. Then what I need to do, I need to go and talk with a program office and ask for permission to let me run that on one of these DoD HPC systems. And the reality here is that these DoD HPC systems, they don't belong to Navy. So some of them belong to Army, some of them belong to Air Force. So if I go to the program office, and if the computer that can do this belongs to Army, most probably they won't let me to do that. And the consequence is that I may not be able to do that simulation at all. And I mean, one typical solution that the programs offer is that they say that, oh, we provide you the money and go and buy this server. And I think this is a source of waste in the Navy. I mean, the reason is that maintaining this system is not easy. So if you ask a local command to take care of this huge system, we ended up with IT issues, and we have seen that many, many times. So anyway, my point here is that the existing quantum computers, one feature of them is that they have this short coherence time. And some people think that this is not a good thing. But for this application, this can be a very good thing because imagine that you have very efficient connection between classical and quantum computers. And we know that they cannot keep the data for a long time. So you imagine that you put it on ACCM data, you process that, and then you put it on this NNPI data and process that. It can help a lot. Let me mention that even if for example, on that 500 standard nodes problem that I mentioned, even if the program allows me to run it on, let's say, Army machines, I have to go through this frontier process. And typically, it means that I start the process 1 year before the real simulation. So if a program asks me, oh, I want to do this change in the design, my answer is that, oh, wait 1 year, I will get back to you. And this is the reality for us. Okay, so I mentioned that why we think that this finite element is important for us, and I mentioned some aspect of it. There are some general consideration about quantum computing, why it is useful. So there are two main aspects that are different with this quantum computing. So one is this fact that with this so-called qubits, qubit is the analog of bit for quantum computer, in case you're not familiar with. So you can store exponential number of values in a linear amount of space. So remember that I mentioned that if you want to simulate a problem of size 2 billion, you only need 31 qubits. And the other one is this entanglement. So this is something very interesting. So if you have multiple bits in a classical system, you can measure them independently, and they don't interact with each other. But with quantum system, if you have multiple qubit system, if you measure the first one, the value of the second one can change. And this is a very interesting property. And if you use that in a, the whole idea of this quantum algorithm is that how you can, in a smart way, use these properties to exponentially speed up. So there are some problems that have shown to gain a lot from this quantum algorithm. So one is this Shor algorithm, famous one for encryption, and the other one is this quantum Fourier transform. But the reality is that most of the problem will not gain any speed up with with quantum computers, and this is something that we should keep in our mind. This figure perhaps is a good figure here. So it shows that this P class here is the problem that we can classically solve with, efficiently solve with classical computer. This BQP is the problems that we can solve efficiently with quantum computers. And you can see that many problems are not in that circle. And this is not a limitation of building quantum computers. This is a theoretical limitation. So even if you have the best computers, still you cannot solve many problems efficiently. And this is a good thing. We can have some encryptions that are safe, quantum safe. So, if you are interested to read something about the limitation of quantum computers, I suggest this reference here by Aronson is a good read. And the other thing about quantum computation is about quantum computers. So I mentioned that, so when people talk about quantum algorithms, they typically think about these fault-tolerant machines. So these are supposed to be large scale and be able to solve large scale and complex problems. And some manufacturers like IBM, they claim that they will be available by 2030, but who knows? And my point here is that if you are using some sort of quantum algorithm that depends on this system, you are not probably thinking on what you can do in a short run. The other systems are those that are available right now, the so-called NISQ computers. The main thing about them is that they are noisy. And they have limited number of qubits, and the connectivity of those qubits are limited. And you can imagine that you cannot implement many problems on these type of systems. So let me also mention some general things about finite element method. So I mentioned that we want to speed up finite element method. Then the question is how we can speed that up. So let me go through quickly main aspect of finite element method. So let's say you want to model, so you have a membrane and you want to model displacement of that membrane. So the first step is that you go to physics and you identify some sort of differential equations that govern the physics of the problem. The second step is that you have a domain, let's say here is a rectangular domain, you consider a mesh for that. And the third step is that based on this mesh, you form a linear system and you solve that linear system. And the last step is this post-processing to get what you really look after. The point here is that the most time-consuming part is the third step, solving that linear system. So one thing that we want to see is that can we speed up finite element by speeding up solving linear systems? And let me mention that there is this paper on a theoretical limit of what you can gain with quantum computing for finite element. It says that you cannot go to this exponential speed up, at most polynomial, which is not bad. Going back to that example, from 2 weeks going to 2 days is still good. We are not looking for going to less than a second. So, our understanding was that we can accelerate a finite element by solving a linear system. Then the question is, what are the existing algorithms for that? So right now, there are two classes of approaches. One is this purely quantum. So these are based on this so-called HHL algorithm. So there are two things here. One thing is that they need very deep circuit depth, which you cannot implement on existing machines. The other concern here is that even if you have this so-called fault tolerant that you can implement this algorithm on that, it is not obvious that you can get any advantage for finite element. So people talk about if you use HHL, you can exponentially speed up solving linear system. But the point here is that typically, if you want to see it, theoretically, if you want to see a speed up with HHL, you shouldn't care about, so when you solve a linear system, you shouldn't care about all component of the solution. For example, you should care about the specific inner product or the, let's say, a maximum component of your solution, not all of them. If you want to get all of them, which is the case in finite element, it means that you should repeat HHL many times, equivalent to the size of your system, and it can diminish all the speed up that you may expect. So there are some questions about HHL here. The other approach here is this hybrid quantum classical. The main advantage of this approach for me is that you can implement them on existing quantum computers. And some of them, like this variational quantum eigensolvers, they have a long history in quantum chemistry. So there are some previous work on them. And our goal here is to see if we can use these hybrid approaches to solve finite element. So if I want to go through the main blocks of this variational solvers, so you have a classical computer and you have a quantum computer. So what classical computer does, it will solve iteratively an optimization problem. So the challenge there is that computing the cost function for this optimization problem is expensive. So that part of the process in each iteration is going to be sent to a quantum computer, and the result will be sent back to classical one, and this process will be repeated until you get the optimal parameters. And the last step here is that you have this so-called ansatz, which is a quantum circuit, depends on the parameter. So you plug in the optimal parameter, and the output of this quantum circuit is a solution candidate. So one thing here is that the depth of this ansatz is typically shallow. Actually, it is the expectation. We hope that it is shallow. And the reason that we can implement that on existing machine is that it is shallow. So based on what I described, so one can consider this framework for quantum classical finite element approach. So you have two machines. You have a classical machine and you have a quantum machine. So a typical finite element can start like this. You create a mesh on your classical machine, and then the next step is something between classical and quantum. I believe it can be put on quantum. So the point here is that when you want to solve a linear system that I talked about, in a quantum way, you really don't need the matrix itself. You need something called Hamiltonian of that system. And the reality is that you don't need Hamiltonian itself. You need a decomposition of that Hamiltonian. So if you find a way for a specific matrix to form that decomposition, you can directly put that on your quantum machine, and you don't need to form that matrix at all. And then the next step is that you have this classical optimizers that will work with your quantum computer to iteratively solve for a system. And if you get the convergence, you get this parameter, optimal parameter here. Optimal parameter is sent to a quantum computer again, and you get the result. And after some post-processing, you get the final result. If it is some sort of nonlinear problem or transient problem, you are going to repeat this process again for each time step. If not, then you are good and you go to post-processing and you can read your result. For this approach to be useful, there are some things that should be realized. One is that, so when we talk about solving a linear system, the right side vector we should be able to read it efficiently into your computer. So this is an important thing. The other thing is this quantum preconditioner. So this preconditioning is something that is well known in classical setting. But in quantum setting, it is poorly understood. So the goal of preconditioning is classical setting, and quantum setting is not the same. you need, so I will talk about that later. But for now, we need a good quantum preconditioner as well. And then remember that I mentioned that you need this decomposition for Hamiltonian. You need a good decomposition there as well. And of course, you need some sort of efficient quantum classical linear solver for this loop as well. The other thing that is important is that when you have your optimal parameter and you want to go, prepare your solution in quantum as a quantum state, and you want to read your real solution in a classical one, this process should be also efficient. That can become a bottleneck for a real system. And the last thing, which is also very important, and I'm going to give some example for that, is this interface between quantum and classical. It should be efficient. If we are going to wait a long time for each iteration, we are not going to get anything in practice. To demonstrate some of the potential challenges that we may face, I'm going to solve a simple equation here. So this is one-dimensional Poisson equation, which is relevant both to elasticity and CFD. So if you try to solve, so the equation is simple. I mean, in one-dimensional case, it's a simple, a second-degree ODE. And what I want to do, I want to use linear finite element to solve this system. To do this simulation of, so I mentioned that we need a classical computer and we need a quantum computer. For a classical computer, we used either a local workstation or this DoD HPC server or IBM servers. And for quantum part, we did two things. So in one approach, we consider these local noise-free simulators. These are implemented on classical computers, and they're supposed to simulate fault-tolerant computers, quantum computers that are not noisy. The second one is we tested on real IBM quantum computers. So if we go with noise-free simulators, so if you look at this, say this figure, what you see is that classical and quantum are doing well, both of them. And when you increase the resolution of your mesh, you can capture the solution very well. So fine, nothing special. Some interesting observation here is that when we talk about, remember that I mentioned that we need some sort of optimizer. There are two types of optimizer, one that depend on gradient and one that don't depend on gradient. This aspect of what I'm saying is also related to quantum machine learning. So consider typical neural network. When you want to train that, people use this gradient-based optimizer like Adam or something. So one observation here is that when the size of the problem is small, basically there is no big difference between gradient-free and gradient-based optimizers. Of course, gradient-based converge a little bit faster, but both are fine. On a noise-free simulator, when you start increasing the size of, when you start increasing the size of a problem, for example, you go to 5 qubits, then typically what you need to do several steps of this gradient-free, and then at the last stage, you do some sort of gradient-based optimization. But there is not a big performance drop for both of them. So before moving on, I mentioned that I care about what we can do with this system right now. One aspect of that is that can we scale up this simulation? So what I presented to you, you can show that you cannot scale this up. So the reason is that there are twofold. The reason one is that so I talked about this preconditioning and condition number, which is an important a challenge. So the way that I pose the problem, the condition number is scaling like N2. So this is a bad scaling. And the other thing here is that I talk about a decomposition that needs to be used for quantum system. Here it is scaling like linear, and again, it is not good. Both of them should this polylog, which is much lower than these. So these are something to keep in our mind. The other thing that I want to say is that at the end of the day, we want to implement them on noisy systems. We don't want to, simulators, and we don't have access to this, fault-tolerant system. One thing that has been observed is that noise can affect the performance of optimizers. So, and that depends on the application as well. So, for example, consider this application, which is quantum chemistry. If you don't have any noise, this conjugate gradient, which is derivative-based, is the best one. But if you consider a noisy system, then conjugate gradient is 8. So one consequence here is that if your application depends on gradient-based optimizers like this neural networks, deep learning, then you may have some challenge with noisy quantum machines. Okay, so the next thing is the simulation that we did on IBM quantum machine. So right now we have access, by we I mean warfare centers of the Navy. We have access to 6 IBM quantum computers via this IBM quantum hub, and it is through a contract that we have, by we I mean Naval Quantum Computing Program Office, with AFRL. To do this simulation, we need a classical machine and we need a quantum machine. So the first thing that we did for a classical machine, we consider a local machine and or a DoD HPC machine. And for a quantum computer, of course, we use IBM quantum machines. And one thing that we observe is that the interface is not practical. So the reason was that, so let's say you want to run iteratively an optimization that involves, let's say, 500 iterations. So the way that it works with older Qiskit runtime was that, so you submit the first iteration and you need to stay in a queue to be able to run that. And when the result is back to your classical machine, you submit the second one, and again, you need to stay in a line. And that is totally different from what you expect from, let's say, classical system. So in a classical system, if you want to run 500 iterations, you just submit everything and, just one queue. But here you have several queues. So recently, we have been told that, IBM come up with this quantum Qiskit serverless approach. I forgot to mention that all this implementation are done with this Python package Qiskit that is developed by IBM. So this idea of Qiskit serverless make it closer to realize some sort of advantage with quantum computers. So the idea is that you have a local machine. You submit your job to a IBM classical machine. And then IBM classical machine will submit the job for you to IBM quantum computers, and it is more meaningful, right? Actually, with the initial process that I mentioned, that for each iteration you have to stay in a line, I could never run more than 50 consecutive iterations, and sometimes that 50 iteration took 5 days, 6 days. But with the new one, we had some success. So let me talk about this figure. So for this simulation that I'm going to show, we use this IBM Brisbane. So this is a typical map that you can get from IBM platform. So this shows different qubits and the connectivity of these qubits. These are the so-called CNOT gates. And when I say that NISQ computer has limited connectivity, I mean exactly this. So for example, this 40 is only connected to 39 and 41. So if you are using some sort of algorithm that needs more than 2 connections to be efficient, then this is not what you want. You need to transpile it to this specific architecture, and you can lose some of the advantage that you can get. And the color here shows the quality of these CNOT gates. So not all of them are good. For example, this one. Okay. And this is a typical result that you may get. So first of all, I was able to run 200 iterations, which was a record for myself, but it took 7 hours. And I'm talking about solving a 4x4 system. So it is a joke, 7 hours waiting for what. But there are some parameters here that can be improved. And one observation here is that I use this VQE. Right now, when people talk about solving linear system with quantum algorithm, they, with this variational approach, they are thinking either VQE or VQLS. But I have an argument that both of them are bad. So this is this is very a small size problem for that by 4. You shouldn't need any kind of trick to solve that. And if you look at, so this green here is the quantum result that you get. And the upshot here is that this VQE is very sensitive to noise. And this is something that we should try to figure out how to deal with. So talking about these challenges, I want to conclude this presentation with a milestone and challenges that we face to get to that milestone. So our goal here is to scale up to 31 qubits. And this is very modest goal comparing to, when you look at, what goals people put, I don't know, several hundred qubits. And at least for our command, I think this will cover nearly all of our needs, and it can help us accelerate our simulation. So some technical challenges here. So the first technical challenge, this figure can help me to explain that. So let's say you have a solution space, and you have a solution, this red dot here. Two common approach, this VQE and VQLS, they cannot touch that. So, depending on the parameters there, they have a representation issue. That means that no matter how much you play with that, you may not be able to capture the solution. This is one challenge there. The other challenge is that this VQE and VQLS have very complex optimization landscape. So either you have too many minimum, or you have this so-called barren plateau where you have some very flat landscape and your optimizer can fail. The other challenge is this preconditioning. So in classical setting, when people do preconditioning, typically they want to find a good condition number, transfer your system to a system with good condition number, and they want to keep some sort of structure, sparsity or something. In quantum approach, we need very specific scaling for condition number, this polylog n. And the other thing is that we don't care about the sparsity, we care about efficient decomposition. And this is a field that is poorly understood. If we want to have a good linear solvers, we need to figure this part out. The other thing is this unitary decomposition. I mentioned that we care about a decomposition of a Hamiltonian, not the Hamiltonian itself. And then the question is, what type of a structure, what classes of matrices admit that efficient decomposition? Again, this is something not very well understood. And the last part is that encoding and reading solution in NISQ computers, we should be able to do it in an efficient way. So by that, for example, let's say you have something, a quantum circuit like this. So you have one qubit that is connected to all other qubits. So it may happen the number of gates are optimal, but the challenge here is that you cannot implement this on a existing quantum computers. You can only implement something like this. And if you want to translate this multiple connection to this sequential connection, you are going to lose some efficiency there. And then, this is the last slide. There are also other challenges. So they were technical challenges. Regarding other challenges, so I think the most important one is collaboration with industry and academia for us. So if you think about what we do, there are three main things that we do. So first is that we monitor application and what is available in the literature and which one is suitable for us. The second one is that we need to implement new ideas, and the last one is testing. So right now, we are pretty good with monitoring, literature review, and also very good in testing, but we are not good at all with implementation. The reason is that we don't have sufficient workforce for that. That's a simple reason. Uh, if we want to get something in the near term, we need to be better in the implementation. So I mentioned that we have this NICE funding, which is some sort of internal R&D funding for warfare centers, but we can't do collaboration with outside entities with this sort of funding. So one thing that I learned throughout the past year was that it is not easy to find funding to collaborate with industry. So I mainly talked to NRL folks, ONR folks, and the problem was beyond that a program manager didn't like my idea. The problem was that the portfolio is small at ONR. So the new leadership apparently had some interest, but still I haven't seen anything on my, command. There is this new Dakar funding announced by Undersecretary of Defense, but the challenge here is that we are in continuous resolution, and we haven't seen that yet as well. So I hope that we can find a solution for that part to work closely with, our academic and industrial partners. And the other thing is this quantum computing resources that we have access to. Right now, we have access to IBM resources. One challenge with this IBM access is that it is not easy for software development, this tool development, it is not easy. So the challenge is that we have limited access and waiting times is typically long. So if you look at this table that I put there, we have different technologies for qubit. So right now we have access to this superconducting technology mainly by IBM Q, but there are other technologies like these trapped ions with IonQ and some other technologies, and nobody knows which of these are better. So right now we are limited to IBM machines, but it is good if we can try other ones. I am aware that AFRL has recently signed a contract with IonQ, but still I haven't seen that. But hopefully there will be some changes on that direction. There are other things like, I think still the quantum classical interface is not efficient. And the other challenge, again, this is something related to the contract that we have. So we have some collaborators, I'm not talking about industry or academia, I am talking about ARL PSU. So they are kind of DoD entity, but and they are collaborating with us, but they cannot use a quantum computer based on our contract, and that is also not really ideal. So if we can find a solution in that regard, would be good as well. So, so in conclusion, so I gave an overview of what we do at Carderock. So I think the main thing was that workforce development is our main thing, one of the main aspects of what we do. So I mentioned that this finite element, more efficient approach for finite element method is something that is important for us. And it will be a good contribution to the modeling and simulation community. So right now I have some customers. If I have this tool, for example, this Create Chip program funded under this DoD HPC modernization program, they are interested in that. So this is something that solves an existing problem. And then I mentioned that these quantum computers can be useful even if we have no speed up. I gave some example. And then I talked about some challenges. I think for me personally, the most important one is that if I can get some extra support to collaborate with academia and industry. So with that, thank you for your attention.
Thank you, Arshan. So, do we have a few minutes for your Q&A?
Sure.
Sure. Any questions from the audience? Please.
So speaking to your workforce development, so I'm curious with what you've discovered so far. So typically when you look at computational numerical solvers and tools like that, when you start having folks from a workforce development perspective try and switch from, let's say, MATLAB to SciPy or some other computational solver, there is a learning curve, but at least architecturally speaking, you're designing your algorithms in the same way. You're thinking about how you're transferring data in and out the same way. It's sort of a traditional computational workflow and process. Is the approach for getting folks up to speed who are used to computational analysis, potentially using some of these tools, should we be taking a similar approach as, oh, I'm just going to learn the syntax and kind of the workflow, or are there different ways we can accelerate the ability of someone to switch from computational to start experimenting in quantum, trying to reach a reasonable time frame, and then adding in some of this urgency discussion that we've been talking about over the next even 3 to 5 years down the road?
Okay. So I mentioned that it is hard to get people for this task. One of them is exactly related to the thing that you mentioned. So for example, in our command, many people like to work with MATLAB, and many people don't like Python. So I learned in a hard way that as a developer, so there are two different things. One is development of a tool. The second one is the usage of that tool. When you design something for the usage, you should keep in your mind that some people only like MATLAB. So sometimes I write a wrapper in MATLAB, because if I don't, if anything happens, a challenge there, I should take care of that, and I don't have that much availability. So I would say that there are two aspects of this. One is the real development, and this is supposed to be done by very few people, not the whole command. And the second is that how we are going to use them. And this should have a good interface for a typical user. And I mean, I mentioned that one challenge is to find some people, some developers. I mean, as you can imagine, people that are handy with different programming language, they are in high demand. So this has been one challenge for me. I hope that I answered your question.
Hey, good morning. My name is Al Lucchini, IT Strategic Planner, Contract Support to Naver. Your second bullet, access to quantum computing resources. I understand AWS has some resources, IonQ, Rigetti. Do you utilize any of those?
We don't have contract with AWS. I like to do that, but we don't have contract with them. So hopefully that may change, but we don't have access to them.
Yeah, part of the reason I wanted to get this on the schedule today is so that we can begin talking about quantum and post-quantum. I mean, we're just on the very leading edge of looking at adopting the technology for the Navy Marine Corps. I believe there's a quantum working group led by ONR. Anybody part of that? Arshang, are you part of that?
So, so this is what I know. So we have this working group, ONR and NISQ PAC. So there is this naval quantum computing program. So and I am also involved with that. Yes, I am.
Perfect. So the whole idea here was an entire day, or as much as we can, on quantum, so we can begin talking about it. My own personal belief is until we start talking about it, we can't start getting the traction, we can't start getting the resourcing, we can't start talking about use cases. So that's what we're really doing here today. Arshang, fantastic brief, very technical, but discussing some of the challenges and that we have. Definitely noisy systems are a big challenge. That's what I continue to hear. Computing resources and funding. So access to funding. So let's stay in touch. And of course, I hope we have more speakers in the room as we go through the day-to-day. And one of the things that I did talk to the ONR lead about was, can we start to build out something that's more of a use case focus discussion rather than just a technical discussion, which is a great basis for the use case discussion. So Arshang, welcome you to be please part of that discussion as we go forward.
Sure.
Thanks so much for your time today.
Thank you. And also, I mean, I was not sure who is the audience for this talk. So if you find this a little bit too technical, my apologies for that.
No. Fantastic. Thanks for the discussion. Clap, please. Thank you, Arshang. So, do we have any presenters in the room today for later this afternoon? All right. So the next presentation is at 10:45. We're ahead of schedule, and that'll be Amazon Kuiper. Mr. Rashid Neighbors and Dave Spencer will be here, and they're going to talk about Amazon Kuiper solutions and also AWS. So Arshang, AWS will be in the room in about an hour if you want to stick around, and we can address those questions. So let's take a break for about an hour. We'll come back at 10:30, 10:40, and we'll do this again. Thank you.